Understanding black holes, the enigmatic giants of the universe. Black holes are one of the most fascinating and mysterious phenomena in astrophysics. They are regions of spacetime where gravity is so strong that nothing, not even light, can escape their grasp. The idea of a black hole often evokes images of cosmic vacuum cleaners, sucking up anything in their path. But in reality, black holes are complex objects that challenge our understanding of the universe, pushing the boundaries of physics to their limits. What is a black hole? At its core, a black hole is an invisible object in space with an extremely strong gravitational pull. It is formed when a massive star runs out of fuel and collapses under its own gravity, creating a point where the density becomes infinite. This point is known as a singularity. Surrounding the singularity is the event horizon, a boundary beyond which no information or matter can escape, including light, which is why black holes are black. Black holes are often categorized based on their mass. There are three primary types. Stellar black holes, these are the most common and are formed when a massive star, at least 20 times the mass of the Sun, reaches the end of its life cycle and collapses into a black hole. Stellar black holes typically have masses ranging from a few to several tens of solar masses. Supermassive black holes, these are found at the centers of most galaxies, including our own Milky Way. Supermassive black holes can have masses ranging from millions to billions of times the mass of the Sun. They are thought to have formed early in the history of the universe, possibly through the merging of smaller black holes or the accretion of gas over time. Intermediate black holes, these are a theoretical category, lying between stellar and supermassive black holes. Evidence for their existence is still scarce, but astronomers believe they may be formed by the merging of stellar black holes or by the collapse of massive gas clouds. How are black holes formed? The formation of a black hole typically follows the death of a massive star. Here's a simplified overview of how this process unfolds. The stellar life cycle. When a star like the Sun runs out of hydrogen in its core, it starts fusing heavier elements like helium. This process causes the star to expand and cool, forming a red giant. For very massive stars, several times the mass of the Sun, this process continues until the core becomes predominantly iron, which cannot undergo fusion to generate energy. Supernova explosion. Once the core's fuel is exhausted, the star can no longer support its own weight. The core collapses, and the outer layers are expelled in a massive explosion known as a supernova. For massive stars, this explosion can lead to the formation of a black hole. It represents the boundary beyond which nothing, not even light, can escape the black hole's gravitational pull. Once something crosses the event horizon, it is inevitably drawn towards the singularity, and its fate is sealed. The event horizon also marks the limit at which the curvature of spacetime becomes so extreme that classical physics breaks down. This is where Einstein's theory of general relativity and quantum mechanics collide, and a unified theory of quantum gravity is required to describe what happens inside. How do we detect black holes? Although black holes themselves cannot be directly observed because they do not emit light, their presence can be inferred by observing the behavior of nearby objects. There are several ways astronomers detect black holes. Gravitational lensing. When light from a distant star or galaxy passes near a black hole, the black hole's gravity bends the light, creating a distorted, magnified image of the background object. This phenomenon is known as gravitational lensing and provides indirect evidence of a black hole's presence. Accretion disks. As matter falls into a black hole, it forms an accretion disk around it. The intense friction and gravitational forces cause the matter in the disk to heat up, emitting X-rays and other forms of radiation that can be detected by telescopes. Gravitational waves. The collision and merger of black holes create ripples in spacetime known as gravitational waves. These waves were first detected in 2015 by the LIGO Observatory, confirming a key prediction of Einstein's theory of general relativity. Gravitational wave detection has opened a new window for studying black holes and their mergers. Stellar motion. The presence of a black hole can also be inferred by tracking the motion of nearby stars. If a star orbits an invisible object in a way that suggests a massive but unseen companion, it may indicate the presence of a black hole. Black holes and time, a mind-bending connection. One of the most mind-bending aspects of black holes is their effect on time. According to general relativity, as an object approaches the event horizon, time appears to slow down relative to an observer far away from the black hole. For an object falling into a black hole, it would appear to freeze in time as it nears the event horizon, never quite crossing it, from the perspective of a distant observer. However, from the perspective of the object falling in, the journey would continue into the black hole, eventually reaching the singularity, where the laws of physics break down. The fate of information, the black hole information paradox. One of the greatest puzzles in black hole physics is known as the information paradox. According to quantum mechanics, information about the physical state of a system cannot be destroyed. However, when matter falls into a black hole, it seems that all the information about that matter is lost beyond the event horizon, creating a conflict between quantum mechanics and general relativity. Recent theories, including the idea of holographic principles and black hole complementarity, suggest that information might not be lost, but instead could be encoded in subtle ways around the event horizon. This remains one of the most active areas of research in modern physics. Conclusion: the ongoing mystery of black holes. Black holes remain one of the most mysterious and awe-inspiring objects in the universe. They challenge our understanding of space, time, and the fundamental laws of physics. Whether through the detection of gravitational waves, the study of accretion disks, or the development of new theories in quantum gravity, black holes continue to be a focal point for scientific discovery and exploration. As we peer deeper into the cosmos with increasingly powerful telescopes and observatories, it is likely that the mysteries of black holes will yield even more astonishing revelations about the nature of the universe and the forces that govern it. Until then, the black hole remains a profound symbol of the unknown, where the very fabric of reality is stretched and tested in ways we are only beginning to understand.